Hey everybody, here I go again answering some of Eliana's questions that she emailed me. Maybe someday I'll get an email from someone else asking me some questions, but for now let's answer hers. So she asked about number 28 here, and she just wanted to make sure she was doing it right, she said. Perfectly good reason to email. And the directions say find the zeros for each polynomial function. Alright. Now the zeros are pretty easy to find when they give it to you in factored form. Okay? So the zeros are x equals negative 1/2, x equals positive 4. Those are two places it hits on the x-axis. Then it says give the multiplicity for each zero. Alright, well the multiplicity for x plus 1/2, for that factor, okay, the multiplicity for the 0, x equals negative 1/2, which we got from the factor x plus 1/2, is 1. The multiplicity is 1, so it passes through the x-axis. For x minus 4, the factor, x equals 4, the 0, the multiplicity equals 3. It's also odd, so it passes through. Okay? In order to bounce off the x-axis like we talked about the other day in class, it has to have an even multiplicity, and this one does not. So I think we did answer all the questions there. Okay, so if you wanted to see something like what that looked like on a graph, the directions did not say to do this, but I can tell already just looking at it that it looks something like, let's see, if I multiplied the x times the x cubed, okay, if I were going ahead and distributing all this, I would get x to the 4th, and I would eventually have a negative 3x to the 4th when I was done distributing. Now, negative leading coefficient, even degree polynomial, we have our marionette, our little puppet guy hanging there, okay? So the limit is negative infinity to the right or the left is another way to look at that. So if I put a 0 at negative 1/2, another one at 4, I know the end behavior looks something like that. Not worried too much about squiggles and turnarounds and all that kind of stuff. Other than that, what do I know about it? Well, it passes through at both points, so I have no idea what it does up here, but it goes up, comes back down, doesn't hit the x-axis anywhere in between, or we would have seen from its factors that it had more zeros. So I know it doesn't cross the x-axis any other times, but I do know it looks something like that. That's all we needed to know. So now, Eliana also asked about number 32, which requires barely any more work, just a little bit of factoring first. See, on 32, the trick is they didn't give it to us in factored form. So we have to see if there's a way to factor that. All right, well, I'm going to take f of x equals x cubed plus 5x squared minus 9x minus 45, and I'm going to take an x squared out of each of the first two terms, leaving me with x plus 5. Take a minus 9 out of the next two terms, also leaves me with x plus 5. Then we pull out x plus 5 only once, leaving us with x squared minus 9, which hopefully you guys notice, oh, I learned that factoring pattern. That's called difference of squares. So I have x plus 5, x minus 3, x plus 3 is my three factors. From here, it's the same problem we just did, except they didn't give it to us in factored form. We had to put it in factored form ourselves, and now it's the same problem, where the zeros are going to be x equals negative 5, x equals 3, x equals negative 3. Each factor occurs only once, so all multiplicities are 1, okay? All pass-through points. if I wanted to graph it, I would have something like this. And I would get, let's see, I know that the zeros are at, let's see, there's one over here at -5, one at -3, one at +3. I know that it is a ballerina in its end behavior because it is a positive leading coefficient and an odd powered polynomial, odd degree polynomial. So it's going to look something like that. Incidentally, I could quickly check if we put in 0 for x, okay, if we decided to find f of 0, putting in 0 for x, you get 0 cubed minus 5 times 0 squared minus 9 times 0. Okay, I just learned something. Everything goes away except the constant term at the end. F of 0 is -45. We just found the y-intercept. Okay, so I also have another point now. I didn't go over this in class, but that's the point 0, 45. I'm previewing what we'll be doing later. Again, this thing passes through at all these points, all the zeros, and it hits the y. There's a better way to say it. All of the x-intercepts are pass-through, and the y-intercept, that's a pass through the y-axis. So with these 4 points and knowing its ballerina end behavior, I know what it looks like. The directions did not say to graph. I'm just previewing what we're going to be doing. You were fine if you stopped over here with naming the zeros and giving all the multiplicities. Now, the next one Ellie asked about was 52. And there's a couple of these we didn't go over in class. I apologize. I gave too many, the problems had more directions than I intended for you to do. I definitely wanted you to do A, because we did that in class. Definitely wanted you to do B. Didn't really want you to do C. Didn't go over it in class, but hey, while we're here. Symmetry, we did not go over. We'll talk about it if it's helpful. Some years it is, some years it's not. If necessary, find a few additional points and graph the function. I'll admit that's ambiguous. What does the textbook mean if necessary? I guess it means if you can't figure out the end behavior or anything else, but I'll go ahead and give it a rough sketch of the graph, not a perfect one. That comes in sometime next week. All right, so I'm going to take, didn't really mean to start with the graph here. Let's do some factoring first. Okay, the first thing I'm going to do is take out negative x. And that leaves me with -6 plus x squared plus x to the 4th. See, I want my highest degree term to have a positive leading coefficient. So I'm going to definitely factor out a negative here. And there's an x in each term. So this becomes -x times x to the 4th plus x squared minus 6. Now there's a trick we can do here. We didn't factor any 4th degree polynomials in class the other day, but there's a trick I'm hoping you saw in Algebra 2, and we'll find out who remembers it. It's a trick that in calculus we call U substitution, where I'm going to take the letter U and say that U equals x squared. Okay, see that x to the 4th can be intimidating. But if U is the same thing as x squared, then x to the 4th becomes U squared. And x squared becomes just U. The minus 6 stays as it is. And all of a sudden, this should start to look a little bit more familiar. And it should look something like U plus 3U minus 2. Cool. Okay, so now we're going to go back to our original problem. And this is going to tell me, bring down the negative x. Okay, so this U is the same thing as x squared. So instead of U plus 3, I have x squared plus 3. And instead of U minus 2, I have x squared minus 2. So this tells me that my zeros are x equals 0, because if x is equal to 0, everything else goes away. X equals plus or minus the square root of negative 3, or plus or minus root 3i. Okay, now these are zeros, but they are not x-intercepts. complex zeros count as numbers you can plug back into the original, and if you've done it right, you will get 0 when you're done. But they do not count as x-intercepts. So over here, I'm going to get x equals just plus or minus root 2. Didn't mention multiplicity, said if necessary, find a few points and sketch the graph. Go ahead and give it a quick sketch. Here's what we know. Okay, its end behavior is, let's see, if I go back and look at the original, the leading coefficient, even though they wrote the leading coefficient at the end, you see how they did that? That was tricky. The leading coefficient is always the coefficient on the highest degree term. So this is a 5th degree term. It's a highest term, making it a 5th degree polynomial, and the coefficient is negative, meaning this is a reverse ballerina. Okay? So its end behavior is something like that. Now the zeros are x equals 0. I'm not graphing the complex zeros, and x equals plus or minus root 2. You know what? It's about 1.4, but I'll just put it there and there. The end behavior is reverse ballerina. I have no idea what it does in between, but I'm assuming it must turn around somewhere, go like that. A lot of cubics look like that. I mentioned in class that if this were 3rd degree, it would have at most 2 turnaround points. The number of turnaround points is 1 less than the degree. This could have as many as 4 turnaround points. I don't really know yet. We'll talk about that more next week, but maybe this thing goes turnaround, 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 something like that. I just don't know. I'll leave it squiggly until we get to how to find those. All right, so those are the questions Eliana emailed me, and I hope they help.